As we earlier mentioned, the aim of the Pca algorithm is to reduce the dimensions of our data without losing much information. Say we have a set of vectors x1 to xm, which are all vectors element of Rn, so they are all n-dimensional vectors. Our aim here is to make sure each of these vectors actually have a reduced dimensions. So the set of vectors x1 to xm actually turn to this new set of vectors x1 to xm, with the difference that each of these vectors now have a dimension d instead of n as it was initially. And note that d is strictly less than n. Let's rewrite down what we just mentioned. So we have that these m different vectors, which are all n-dimensional, are going to be converted to these m different vectors, which are d-dimensional. So we have our vectors x1, which is this x1, which is this, x2, which is the next, up to the vector xm, which is this. Notice that each of them have n different elements, as we can go from 1 to right up to n. And so they are all n-dimensional vectors which form this matrix. But now, here we have x1, which is d-dimensional, so we can go from 1 to d. So if n, for example, is 4 and then d is 2, here you're going to have 1, 2, 3, 4 different columns, and here you're going to have just 2 columns if d equals 2. So we have x1, we have x2, and finally xm. Now x1, x2, x2, xm are d-dimensional vectors. Let's look at this problem. Suppose we have these m vectors x1, x2 to xm, which are all 3-dimensional. So in this case, we can take n to be equals 3. Say we want to reduce the dimension of this, or the dimensions of this data, such that the n-dimensional vectors tend to a d equals 2-dimensional vectors. You may think that this can be achieved by just taking off one of the dimensions, but this is not actually the best solution, because taking off one of these dimensions will make us lose so much information contained in this data. So instead of doing that, we could construct a new data set where these vectors, instead of just being made of one of the 3 components, are made of instead 2 of the most important components. By 2 of the most important components, we aren't saying here that we are going to select between, say, the first, the second, and the third component to choose the 2 most important components. Instead, we are going to go to the Pca algorithm to extract these 2 most important components, and that's why we call this now x1 Pca and x2 Pca. Note that we still have our m vectors, and now instead of n equals 3 dimensions per vector, we have d equals 2 dimensions. So we have for each vector x1 given to us as x, big x1, big x2, big x3, which actually forms a vector, say x1 or x2, that's small x1 like this. This is transformed to an x1 Pca, x2 Pca, x3 Pca. And then from here, we sort these components. So suppose we have x1 Pca, which actually is more important than x2 Pca, and x2 Pca more important than x3 Pca. In this case, we shall move from x1, x2, x3 to a new vector which is made of just x1 Pca and x2 Pca. So we can have that. If we are interested in taking or extracting 2 components from this 3, we're going to have x1 Pca, x2 Pca. So our new vector will be made of x1 Pca, x2 Pca, and that's because they are the 2 most important components out of the 3. And if we're just looking for just one component, then we'll go for the most important component, which is x1 Pca. Let's now see how we get x1 Pca, x2 Pca, and x1 Pca if we have these 3 different elements. Suppose we now have several points in a three-dimensional space. That is, this point, for example, is represented with three elements, x1, x2, and x3. Same as this point, this point, this point, this point, and this other point. And that's why we say they are in a 3D space. Now, we can define a 2D subspace like this plane on which we can project each of these points on. So we project this first point on our subspace and we leave from this point to this point on the subspace, next, and this point, and this other point, and finally this other point. So we see that all these points are projected on this 2D subspace. Now, looking from the perspective of this 2D subspace, which is this plane, we can have this with x2 and x1 Pca. So here we can represent these points, that is this point is this other point is this 3 points, this 3, and this other point, this point. So here we've represented these points which have been projected on this plane on this new space, which in fact is a 3D space. We see how we can leave from a vector or vectors which are 3-dimensional to vectors which are 2-dimensional just by projecting them on a 2D space. And then, if these vectors are in a 2D space, they can also be projected on a 1D space. A common example of a 1D space is a line. Say we have this line, we can project all these points which are represented by two elements on this 1D space, which will make them to be represented by just one element. So here we can have this point projected on the space, this point projected, this other point projected, this, and that. So finally, all the points have been projected on this space. And with this, we can form this 1D space, which now contains all these points. So we have this point, which is this here. We have this 3 points, which are here. We have this point, which is this. And we have this other point, which is this. Now, these vectors can be represented by just one element. So they are in a 1D space, and that's it. We've left from this 3D space to this 1D space. The next question will be, how do we do these projections without losing much information? And that's where the orthogonal projection comes to play. We call that the minimum distance from a point to a subspace is the distance from that point to its orthogonal projection on that subspace. So, leaving this point to the subspace, the shortest possible distance is that distance such that this vector is perpendicular to the subspace. And this we are seeing in the linear algebra course. Suppose we have a base B made of D different vectors and H a subspace of Rn, with B being a base of H. X is an element of Rn, and so the projection of X on H, which is the subspace of Rn, is given as B times B transpose X, which is true when this base B is an orthonormal base. So, in this case, where we are trying to project this point, which is an element of R3, since we're in a 3-dimensional space, onto this subspace, which is represented by this plane, which has a base made of two vectors, at least B1 and B2. So here we shall be having B equals B1, B2, and H, a subspace of R3, with B being equals a base of H, where X is an element of R3. So in that case, we're going to be having that the orthogonal projection of each of these points, like say any point X, on the subspace represented by this plane, which is a 2-dimensional subspace, is equals B, which is made of B1 and B2, times B transpose times X, where this is an orthonormal base. And this is equals B times alpha, where alpha is equals B transpose times X. This can be rewritten as alpha 1 times B1 plus alpha 2 times B2 up to alpha z times bz. So since we have written this orthogonal projection as a linear combination of the vectors which make up this base B, we have that the coordinates of the orthogonal projection of x on the subspace H in the base B is actually alpha, where alpha is equals the vector made of the elements alpha 1, alpha 2 up to alpha z. So this is what we have. Let's take this example. Suppose we have these 4 vectors which are actually in a 3D space. We want to project them orthogonally on some 2D space. We have here x1, which is this vector 1, 0, 1, x2, 1, 2, 2, x3, 2, 1, 4, and x4, 1, 1, 0. Here we have a subspace H of this vector space R3 and B a base of H. So we have B equals B1, B2, which is this and this. Now, we are going to select this B1 and B2, making sure that they are actually orthogonal to each other and their norm is actually 1. So that makes B an orthonormal base. X is an element of R3, and the orthogonal projection of X on H in the base E or in the canonical base is B times B transpose times X. Let us now orthogonally project all of these points. We have seen that the orthogonal projection of X on H in the base B itself is B transpose X. So here we have this, which is alpha, which is B transpose X, since alpha is B transpose X. So here we have the orthogonal projection of X1 on H is B transpose X1. Now, what's B transpose? We'll simply find the transpose of this, the resultant matrix from this base, which is going to give us this. So we have this first column, which becomes the first row, the second column, which becomes the second row. This gives us B transpose, and here we have X1, which is this. So multiplying this gives us this. Now notice that this gives us a vector which is actually 2-dimensional, that is in R. And this now are the coordinates of x1 in this subspace. In this subspace, being a 2D subspace, x1 just needs 2 elements, that is 2 coordinates. So x1 now is 205, 1 instead of 101, which it was before. And then the orthogonal projection of x1 on the subspace H in the canonical base is B times B transpose x1, which was given before. Here we'll simply multiply B with B transpose x1. So here we have B times this, which gives us 0.8, 0.41. So these are the coordinates of x1 in the canonical base. So as an example, we have, say, we have this point, which is projected on this base or on this plane, which gives us this other point. Now, this point has coordinates in this 3D space, which in this case can be say this 0.8, 0.41. But in this 2D space, which is this plane, which is actually this, it has actually 2 coordinates because this is a 2D space. And in this case, these coordinates are 205, 1. So this is actually the logic behind leaving from this 3D space or this 3-dimensional vector to a 2-dimensional vector, which is now this. We can move on to x2. The orthogonal projection of x2 on H in the base B is given as B transpose x2, which is this times 1, 2, 2. This is x2, and this is equals 405, 2. And then this orthogonal projection in the canonical base is B times B transpose x2. So simply multiply B with this, and this gives us 1.6, 0.8, 1. So in the canonical base, it has this coordinates, whereas in this base made of just 2 vectors, B1 and B2, its coordinates are 405, 2. We can go on with x3, and then finally for x4, its coordinates in the base B are 305, 0, and its coordinates in the canonical base are 1.2, 0.6, 0. Let's now summarize what we've just done. We've just seen that given this 4 different vectors, which was initially this, we can now form this other 4 vectors now, but which have actually 2 coordinates, which are now vectors in a 2D space. So we have this 1, 0, 1 turn into 205, 1, which is now this. We have 1, 2, 2, which is going to turn into 405, 2, which is going from here. 2, 1, 4, which turns into 505, 4, which is this. 1, 1, 0, which turns to 305, 0, which is this. So this is how we can turn this into this 2D space without losing any much information, and that's because we are actually using the orthogonal projection, which guarantees us that it's the minimum distance from any point to that subspace. The next and the last question we shall be asking ourselves is, how then do we choose this B? Because in this case, this B was arbitrary. All what we did was we made sure it was orthogonal, or the 2 vectors were orthogonal to each other, and the norms were 1. But now, how do we choose this B? That's the next question we shall be answering. But before going on to find the optimal B for each data set, we have to take into consideration the fact that these points, when projected on this new space, don't have to change their positions so much. That is, they have to be projected on this new space, but with a minimal distance from their original position. In this case, we have 1, 0, 1, which is going to leave to go to the next point, 0.8, 0.4, 1. We see that the 1 is maintained, but the 0 goes to 0.4, and the 1 goes to 0.8. And then 1, 2, 2, which goes to 1.6, 0.8, 1, and then 2, 1, 4, which remains at 2, 1, 4. And then 1, 1, 0, which goes to 1.2, 0.60. So let's see whether we can be able to define a new base B, which actually will make these vectors, or each and every one of these vectors, go to a new point which is not very far from it, or which is actually closer to each of these vectors as compared to how close these vectors are to each and every one of these vectors. So to do this, we can ensure that the square of the L2 norm of each and every x and its projection is minimized, such that when you sum up all these distances, we shall have a value as close as possible to 0. Say we have this base B, which is a base of H, and H the subspace of Rn. The B optimal can be gotten as the argmean of the sum of the square of the L2 norm of the distance between xi and its projection on the subspace H. If you're not used to this argmean notation, you can understand this as the value of B for which the sum is minimal. And that value of B is what we term B optimal. B optimal can be written as argmean of B, the sum of this L2 norm square of xi minus B times B transpose xi, and that's because the orthogonal projection of xi on H is B times B transpose xi. And since B is an orthonormal base, let's look at some examples of this. For the example we had previously, we had the 4 vectors x1 to x4, which were all 3-dimensional vectors. Here we have x1 minus its projection on H, that is orthogonal projection on H, with the L2 norm squared, which is given as this x1, which is 101, minus B times B transpose into 101. We had calculated this previously, and it gave us 0.8, 0.41. So we have this minus this, L2 norm square, all of that squared. And this L2 norm is given to us as 1 minus 0.8 square plus 0 minus 0.4 square plus 1 minus 1 square. Given that we have a square, the square root is cancelled, and this is what we have. And for x2, we have 1 to 2 minus 1.6, 0.81, which is equals 1 minus 1.6 square plus 2 minus 0.8 square plus 2 minus 1 square. and all of that is summed up. And then x3, and finally for x4 we have 110 minus 1.2, 0.60, where we have 1 minus 1.2 square plus 1 minus 0.6 square plus 0 minus 0 square. So what we're actually finding here as a sum is actually adding up all these four terms. And this gives us 0.2 plus 2.8 plus 0 plus 0.8, which is actually equals to 3.8. So this means with the base we had chosen, we get this sum as 3.8. What if we choose another base which will give us this sum being a value less than 3.8? That will be more beneficial to us as less information will be lost. Let's rewrite down this equation. Note that we have the Frobenius norm of a minus b squared, that is the square of the Frobenius norm of a minus b, which is equals the sum of aij minus bij, all of that squared. So we're actually taking each element of the matrix A and subtracting it with its corresponding element and squaring and then summing them up. So that's the Frobenius norm. This means if we have this R data set, which is now rewritten as such, well, here we have A transpose, where A transpose actually represents all the vectors in our data set. Recall we had this as x1, we had this as x2, we had this as x3, and we had this as x4, and minus b transpose times each and every one of this. So what we are doing is all these operations which we've done, we're joining it into just one operation by stacking up all the vectors in our data set. So this gives us this minus b transpose times this, which is now equals this. B transpose times all of this should give you 0.8, 0.41, 1.6, 0.81, 214, 1.2, 0.60, which is what we got previously. And from here, we can see that finding the Frobenius norm of the resultant matrix and squaring will give us the same answer as this 3.8. And that's because here we're going to be having 1 minus 0.8 square plus 0 minus 0.4 square plus 1 minus 1 square plus 1 minus 1.6 square plus 2 minus 0.8 square plus 2 minus 1 square plus 2 minus 2 square plus 1 minus 1 square plus 4 minus 4 square plus 1 minus 1.2 square plus 1 minus 0.6 square plus 0 minus 0 square. And you should have noticed that all what we've just listed up now is actually corresponding to these different operations which we had done before. And now this is given as a Frobenius norm instead of the L2 norm we had earlier talked of. And with this, we can say that this B optimal can be written as the argmean B of the Frobenius norm of A transpose minus B transpose times A transpose, where this A actually represents the data set. Before continuing, we shall take note that B transpose B is equals the identity matrix, and this is because B is an orthonormal base. Now, the Frobenius norm square of any matrix is actually equals the trace of the product of the matrix transpose times the matrix itself. So in this case, the Frobenius norm square of the matrix A transpose minus B transpose A transpose is the transpose of A transpose minus B transpose A transpose times itself. So this is what we have. So the Frobenius norm of A, for example, is a trace of A transpose times A. But in this case, A is represented by this matrix. So this is what we have. And this is equals argmain of B, the trace of A minus A B transpose. Now, the reason we have this is simply because A transpose is A, and B transpose A transpose has a transpose which is the same as A B transpose. Now let's look at this a bit more detailedly. What we have in here is we have B transpose A transpose, and we're trying to get this transpose. Recall that the transpose of A, B, and C is C transpose times B transpose times A transpose. So the transpose of this is actually A transpose transpose, which is A, times B transpose transpose, which is B, times B transpose, which is B transpose. And that's how we have this. And also take note that A plus B transpose or A minus B transpose is A transpose minus B transpose. That's why all of this is giving us this. And then here we will write simply what we had here. And from this, we can now multiply these terms. We have A times A transpose, which is this. We have A times B transpose A transpose, which is minus this. We have B transpose times A transpose, which is this. We have B transpose times this, which gives us this. So we have this part, and then we have this other part, which is this. Now, making use of the fact that B transpose B is the item in the matrix, we could simplify this. So here we have this, and B transpose the item in the matrix. This is actually equals admin the trace of A transpose, which is going from here, minus B transpose A transpose, which is from here. Oh, sorry, from here. Then these other two terms actually cancel out, because here we have B transpose A transpose, which is with a negative sign, plus B transpose A transpose, which is the same as this. So this cancel out and giving us now this minus this simply. This is why we have this. But then this admin transpose we're trying to get is actually dependent on B. So what we're trying to find here is the optimal B, which will make sure this term is minimized. And this actually means that if we have any term which doesn't have B in it, it means that term wouldn't help us in minimizing this, or wouldn't help us in getting the optimal B, because we're actually looking for those terms which are a function of B, which can get minimized when we modify B. So that's how we eliminate this term concerning A transpose, because it doesn't contain B. And so from here we have that this admin is equal to admin B of the trace of minus B transpose A transpose, simply because this term doesn't contain B. And then we're working on the cyclic property of the trace operator. We have here that the trace of ABC is actually equals the trace of BCA, which is equal to the trace of CAB. Now, this are not actually equal the trace of, say, BAC, and that's because BAC doesn't respect the cyclic property. Let's look at this. Here we have ABC, so we've decided to move in this direction, so we could draw a circle that's in the clockwise direction going ABC like this. Now, BCA, if you notice, if we go in that same direction, starting from B, we have B, C, and then A, which is in the same direction, and CAB, which is C in this direction, A and B. So we have this. But then, if we want to consider, for example, BAC, you have to do BAC. So you'll be going in the opposite direction, that's an anti-clockwise direction, which is not in the same direction as this. And that's how basically we do to know whether the trace of, say, these three matrices multiplied together are actually equal or not. Let us do the same here. We have B transpose A transpose. This is equals B transpose A transpose AB. That's the trace of this is equal to the trace of this. Let's keep the negative sign out of this for now. We have this B transpose A transpose. Now, if we start looking from B transpose, or if we start from here, we have this on the clockwise direction this way. So we have B transpose A transpose. Now, if we want to look from B, we have B transpose A. So this trace is equals B transpose A, which is also equals B transpose AB. And that's exactly what we have here. And that's because doing this B transpose AB actually flows in this our cycle, which is in the clockwise direction. And that's how we have this. Now, the negative sign disappears. And since the negative sign disappears, we move from argmin to argmax. So instead of wanting to minimize this, we are now trying to maximize this because we have taken the negative sign. We redefine our B optimal as basically the B which will maximize the trace of B transpose AB, where A is actually our data set and B is the base on which we are projecting each point on our data set on. Let's note that A transpose A, all of this transpose is actually equals A transpose A. That is, if we want to get the transpose of this, we'll take this, we'll find this transpose times this transpose. Now A transpose is this, and A transpose is A. So this equals this. This means that A transpose A is a symmetric matrix. And since this is a symmetric matrix, we had seen also before that symmetric matrices are orthogonally diagonalizable, where there exists a B or whatever matrix such that B transpose times the symmetric matrix, which in this case is A transpose A, which is this, times that matrix B, is equals a diagonal matrix, which in its diagonal is made of the eigenvalues of this matrix A transpose A. Since A transpose A is symmetric, it can be written actually in this form. And note that this B forms an orthonormal set of vectors, that is, columns are orthogonal to each other and have norm of 1. Also note that B is made of the eigenvectors of the matrix A transpose A. Now this B optimal equals this can be written as B optimal equals the Argmax B of the trace of the diagonal matrix made of the eigenvalues of A transpose A. So this can be replaced basically with this. Now, knowing how diagonal matrices are written, we have something like this. We have the trace of lambda A transpose A, which is the trace of this, where we have this lambda 1 to lambda n, which is actually made of the eigenvalues of A transpose A, where the trace of this matrix is basically given by adding up all these diagonal elements, and this gives us lambda 1 plus lambda 2 plus lambda 3 up to lambda n, and that's how we get the trace of this matrix. So here we are trying to say that to optimize B, or to get the best possible value for B where this difference is minimized, we have to make sure we maximize these eigenvalues. So in conclusion, we have to choose B such that the eigenvectors of A transpose A are corresponding to the biggest eigenvalues. This is true since we are already saying that this B actually corresponds to the eigenvectors of A transpose A. So to maximize this, we'll simply select this eigenvalues or the eigenvectors which will maximize this eigenvalues. Also note that the matrix A transpose A is known as the covariance matrix, but since we are trying to apply our knowledge of linear algebra, we are avoiding any other terms out of the scope of linear algebra, since the covariance matrix is treated in a probability cause. Now, also in most literature, you will note that many authors say B optimal is given as the eigenvectors of A transpose instead of A transpose A, corresponding to the biggest eigenvalues. This is not actually different from what we've just said. The only difference is that we're considering our A to be an m by n matrix, whereas in this case, A is considered to be an n by m matrix. So when the vectors of your data set, say in this case we have this x1 which is 101, 122, 214, and 110, all make up the rows of your data set. That is, here we have 4 rows. In this case, our data set was made of an m by n matrix where m equals 4 and n equals 3. So we had a 4 by 3 matrix. In this case, we use A transpose A. But if these vectors instead make up the columns of your data set, you instead have to use A times A transpose, and that's what differentiates these two. Let's now take an example to see how to obtain the B optimal when given A, or when given a data set. We had this our previous data set made of 101, this, which was a 4 by 3 matrix. So our vectors, we have 4 vectors, and each of these vectors are represented in 3 dimensions. If it were this case where we're working with A times A transpose, this will instead be A transpose. That is, we're going to have 101, 122, 214, and 110. So each and every row here will instead be a column. Now let's proceed. From here we have that A transpose A is given to us as the transpose of this, which is this times this. Now multiplying, you should be able to have this 3 by 3 matrix, which gives us 7, 5, 11, 5, 6, 8, 11, 8, and 21. Once we have this, we can go ahead to find the eigenvalues. Let's note P to be equals A transpose A to simplify our calculations, or to make our notations less complicated to work with. So we're looking for the determinant of A transpose A minus lambda I3. Actually, what we're looking for here is the eigenvalues of this matrix A transpose A, and A transpose A is P. So the determinant of P minus lambda I3 equals 0 implies that we have the determinant of this P minus lambda I3, which is this, equals 0. And this implies that we're looking for the determinant of this and equating this to 0. So here we have 7 minus lambda times 1, which is 7 minus lambda. This remains intact because here we're going to have 0. We'll go to the next diagonal. Here we have 6 minus lambda, and here we have 21 minus lambda. So we are equating this to 0 in order for us to get the lambdas, which is actually the eigenvalues. Now, rearranging this, we have 7 minus lambda into 21 minus lambda times 6 minus lambda minus 8 times 8, which is 64, and that's how we have this. And then going to the 5, we have negative 5 into 21 minus lambda times 5 minus 11 times 8, which is 88. So that's how we have this. And finally, we have plus 11 into 8 times 5 minus 11 times 6 minus lambda. And that's how we have this. We equated this to 0. We rearrange again. We rearrange, and then we have this. So here we have lambda minus 30.64 into lambda minus 0.8 into lambda minus 2.55. Don't also worry about calculating this by hand. If you're given this to be calculated by hand, a simpler equation will be given to you, not one where you're going to be having this decimals. But if any question given to you, you can basically apply this using the Python programming language, MATLAB, or any other programming language to get this automatically without doing this by hand. So don't worry yourself if you're scared of being able to have this decimal values. And from here we have that our 3 eigenvalues are 30.64, 2.55, and 0.8. And their corresponding eigenvectors are V1, which is the 0.45, 0.35, 0.81, this V2, which is this, and this V3, which is that. Note that if you have the corresponding eigenvectors and they aren't orthogonal, it's important that you go through the Gram-Schmidt orthogonalization method to orthogonalize them, and then you orthonormalize them. In this case, we've already done this. So here we have 3 orthonormal vectors. And then coming back to how to obtain B optimal, we had said that B optimal is gotten by getting the eigenvectors of A transpose A corresponding to the biggest eigenvalues. So if you want a base B made of just 2 vectors, which will permit you leave from this 101, for example, to a 2D space which is gonna have just 2 elements, you obviously need 2 vectors in your base. And if you have to choose 2 vectors, you can't be choosing this vector with 0.8. So you can't be choosing this before this. You have to choose these vectors depending on their eigenvalues. So in this case, since the biggest eigenvalue is 30.64, the very first vector we choose is v1. And then since the next is 2.55, the second next vector we choose is this v2. So in order for us to choose a base b, which will permit us leave from this to a 2D space, we're going to choose these 2 vectors, v1 and v2. In the case where we want to leave from this to a 1D space, we just have to choose this one. So if we want to form a base from these 3 vectors, the very first 2 vectors we can choose are actually this and this. And so we can form this. If we want to convert each of these vectors to a 2D space, that is to 2D vectors, we're going to have this. And then if we were to select the next such that we are converting these vectors to a 1D space, we have to eliminate this such that we'll be left with this. And that's what we have. And so with this, we'll see how to obtain B optimal. We shall continue with our initial example and see how this new choice of B is going to affect the difference between each point and its projection. We had the projection of x1 on H. The base B is given as B transpose x1, which is now this because we have chosen B to be the transpose of this matrix. So we have B transpose, which is this, times x1, which is now this. And this gives us this new point, 0.899, 0.347. And then in the canonical base, this is equals B into B transpose x1. This is B, and this is B transpose x1, which is this. And this gives us this point, or this vector. Then the projection of x2 on H is given as this. The projection of x2 on H in the canonical base is given as this. We have for x3, and then finally for x4. So we have projected all these points in our 2D space using the base B, which is made of the 2 most important eigenvectors of B. So to convert these vectors 101, 122, 214, 110, which are part of this data set, into our 2D space using B, we actually get to these other points instead of the points we had initially when we took an arbitrary B. So we now have these points, and then we can do this. We have this x1 minus its projection in the base E, which is the canonical base, the norm squared, which gives us this minus this. This is gotten actually from here. And then we have 1 minus 0.37 or 0.38 squared plus 0 minus 0.01 squared plus 1 minus 0.88 squared. And this is equals 0.3989. And then for x2, we have 1 to 2 minus 1.37, 1.84, which is this. And then we have 0.176. And then here we have this, which gives us 0. And here we have 110 minus this, which gives us 0.3689. Now, let us sum up all these differences and compare with what we had initially when we had just chosen an arbitrary B. Summing this up, we have 0.9447, which is actually less than 3.8, which is what we had previously. And this tells us that actually making use of this new base B made of 2 vectors, which were actually this and this, makes us not only reduce the dimensions of our vectors as in 101 to this 2D space, but also make us lose as less information as possible. So, and then finally, if our base is made of just 1 vector, we can convert each of these vectors to these vectors, which now are in a one-dimensional space. Now we've seen exactly how the Pca algorithm works. We've studied the theory behind this, we've taken some examples, and now we are ready to take some practical real-world examples.